Hey, Don Davis, Professor of Mathematics, back with you. And here we are moving on to Chapter 2 on descriptive statistics. Now, descriptive statistics is basically a way that we can describe what's primarily a sample of data. And we're going to do that two ways. First, we're going to talk about how to describe data graphically through charts and graphs and that kind of thing. A lot of the things that a lot of people, when they think of statistics, that's what they normally think of. And then we'll talk about the numerical descriptive statistics, how we can use numbers to describe a sample of data. But before we do that, kind of have to do a preliminary here and talk about properties of frequency distributions. In other words, how do we just organize data to begin with? So let's go ahead and get started on that. First, we can describe a frequency distribution as a table that lists the categories of data along with how often the categories occur. Now, first off, remember, you see that handwritten font. That means you want to write this down. And whenever we see the word distribution in statistics, we mean a table. So what we're talking about making here is a frequency table. Now go over a few notes here. Now, these categories that the frequency distribution make up, those are called the classes, the different classes of a frequency distribution. Those kind of go across in the rows. And the class frequency, that shows how many data items fall into each class. All right? The number of occurrences of each data item. So there is basically two types of frequency distributions. Let's go ahead and start to take a look at those now. The first type of frequency distribution is called the ungrouped frequency distribution. And we can think of that as a frequency distribution that summarizes the frequencies of categorical data. So remember from Chapter 1, categorical data is data that we can put into groups, and we can see how many of them there are, but we can't really do anything else with it. Basically, non-numeric data. Let's take a look at an example of one of these ungrouped frequency distributions here. How about this? In a sample of 75 hospital admission forms, the marital status of each patient is recorded. The results are shown in the frequency distribution. So take a look here. What we have is an ungrouped frequency distribution. All right. In other words, there's four classes: one for single, one for married, one for divorced, one for widowed. Four classes, and there we see three of the classes. We know what the frequencies are. Now it says determine the number of admission forms that had the marital status of widowed. All right. So notice here. What do we know? We know the frequencies of these three classes. Frequency, we're denoting that with an F. This one's missing. But what we do know is the total number of admission forms. There were 75 of them. So let's go ahead and solve this now. Let me first off, let me just grab a piece of paper here so we can write some things down. Well, so think of what we know here. Let's let F be the unknown frequency. So we know if we take 31 plus 23 plus 14 plus our unknown frequency for the widowed people, that's F, what do we get there? We're supposed to get 75 altogether. So let's just do a little bit of algebra here. To solve for F, we want to subtract these three numbers on the left. So that means F is going to be equal to 75 minus 31 minus 23 minus 14. So let me grab my calculator here and figure out what that number is. So we have 75 minus 31 minus 23 minus 14. So there we go. It looks like that missing frequency for the widowed and the marital status was 7. So let's just go ahead and make note of that, and then we'll kind of make some conclusions based on this. All right? Found out it was 7. So a couple observations here. First, the total number of admissions, that's called the sample size. There it was 75, wasn't it? And we'll denote sample size with a lowercase letter n. So whenever you see a lowercase letter n, that means that's the size of our sample, the number of sample observations. We can get the sample size by adding the frequencies together. In other words, let me put that, take that and put that in words. The sum of the frequencies is equal to the sample size. So the sum of the frequencies in one of these frequency distributions, we have an ungrouped one here, that gives us the sample size. Now, let's write that same thing mathematically now. Now, whenever you see the Greek letter sigma in mathematics, that means the sum of. In other words, add some stuff up. So to say that the sum of the frequencies is equal to the sample size, we'll write this. Sigma f equals n. In other words, the sum of the frequencies is equal to the sample size. So that's, I think of that, I guess that's the first formula we've had in our class, isn't it? All right? Sigma f equals n. The sum of the frequencies is equal to the sample size. Now, let's talk about some special frequencies here. First, we can say that the relative frequency of a class is the class's frequency divided by the sample size. In other words, let's put that in terms of a little formula here. The relative frequency of a class, I'll put RF for relative frequency, that's equal to the frequency of the class divided by whatever the sample size is. All right, so this gives us the proportion of each class for the total of the number of observations in the sample size. All right, and so consequently, we write the relative frequency as a whole number percentage, or we could put, round it to 1 decimal place, however we're specified to do it. All right, whole number percentage is the most common way to do it. So let's take a look at this example here. It says determine the relative frequencies for the frequency distribution in example 1. Now I went ahead and put in that 7, that missing frequency we had. And so let's start computing these relative frequencies here. So for the first class, we want to take of the single people, we want to take the frequency of that class, that's 31, divide that by the sample size, 75. All right? So just to remind us here, that's the class frequency divided by the sample size. In other words, the sum of the frequencies. So let me grab my calculator here. Let's go ahead and compute that. Now, we did this calculation earlier, remember? To clear that out, I'll just hit the AC all clear key. So now we want to make a fraction that looks just like the one we wrote down by hand. So use this little fraction key right underneath where it says ABS. We'll get to that later. See the little fraction key right there? I'll just click on that and we'll put in 31 and then hit the right cursor key and then put in 75. So that's how we enter one of these fractions, in this case a proper fraction, into our calculator. Go ahead and hit equals, and now we want to make that in decimal form, so let's just go ahead and hit this key here. See, this says SD standard to decimal. Okay, I'll go ahead and click on that, and that's what, 0.4, 1, and then 3 repeating. All right? And so rounded to the nearest whole percentage, that would be what? We have to move the decimal 2 places to the right. Remember doing that? So that would be 41%. Let me do the next one here, make sure we have the idea. The frequency of the next class is 23. So I'll hit the fraction key again. 23 divided by 75, our sample size. Hit equals, and then hit that SD key one more time. So that would be 23 divided by 75, and that would give us a relative frequency. It looks like it would be 31% when rounded to the nearest whole decimal place. All right? So I won't bore you with the rest here. We'll just go ahead and move on. You can do that. Certainly you can handle that on your own. So there's the completed frequency distribution with the relative frequencies included. So we can see the relative frequencies of the last 2 classes were 19% and 9%. Now before moving on, let's just make one more quick observation here. Notice what happens if I add up all of these relative frequencies. Notice what we get would be, what, 98%. Now notice here, Why would that happen? Well, that could happen from some rounding involved here. Rounding to the nearest whole number. So my point being, theoretically, you would think these would all add up to 100%, but sometimes it doesn't, and that's due to rounding. So that's okay. Don't let that bother you. Just make sure that you're consistent in doing the rounding here to the nearest whole number decimal place. All right. So it could be off. It could be 101 if you add them all up. Depending on the rounding. But what you don't want to do is to start to fudge with these numbers to try to get it to add up to 100%. All right. So that's the grouped frequency distribution used with categorical data. Now let's take a look at our second type of frequency distribution here. We can say that a grouped frequency distribution summarizes the frequencies of quantitative data, in other words, numerical data. And we call it a grouped frequency distribution because we have to cluster our data into groups. Each class has a beginning and an ending value. We call these beginning and ending values the class limits. Now, the smallest value for a data item in a class is called the lower class limit. All right, LCL you'll see sometimes written, the lower class limit. The largest value in a class is the upper class limit, the UCL. Now, here's a real important property, a definition we want to know. The difference between any two consecutive lower class limits gives us the class width, and we'll denote the class width with CW here. All right. Now, let's say we have a set of sample data, and we want to determine what the class width would be. Let's talk about how we can go ahead and set that up. We can say that for a set of given sample data, if the desired number of classes is given, we set the class width to this. We take the largest value in the data set, subtract the smallest one, and then divide that by the number of classes. All right, and then we'll get some sort of number, and it'll usually have a whole number part and then a decimal number part. And what we want to do, we want to round that number up to the next higher whole number. All right, that guarantees that we have a class width wide enough to cover all the sample data that we have. All right, so round up to the next higher whole number. A couple other observations here in terms of setting a class width. If the number of classes is not specified, you might want to use a convenient class width, like increments of 2 or 5 or 10, that kind of thing. Start with the lower class limit and add the class width successively. We'll talk about that in just a minute. Also, we want to, generally when you're making a grouped frequency distribution, we want to keep the number of classes somewhere between 4 and 10. Any fewer than 4, and you really can't tell what's going on with the distribution of the data graphically. Any more than 10, well, it's just so tedious to work with. So let's take a look at an example of one of these, setting up one of these grouped frequency distributions. Let's suppose we want to construct a frequency distribution of ages of birth starting at age 0, age of birth, and use a class width of 20 years. Write the first 5 classes of the distribution. All right, so here we go. I went ahead and set that up. Here are the class limits here. Let's see how we get them. So what did we do? We wrote down the lower class limit to coincide with the smallest value we have. And then what did we do? We added 20 successively, and I did that over here. We added 20 to get the lower limit of the second class. We added 20 more to get the lower limit of the third class, added 20 more for the next class, and so on. So notice here, we successively added the class width to get the lower class limits. Now to get the upper limits, what did we do here? We took the lower limit of the next class and subtracted 1. Lower limit subtracted 1. So the upper limit of the first class is 19, and then 39, and then 59, and then 79, and so forth. Notice that also one of the properties of class width is that the difference between any two consecutive upper class limits also gives us the class width. All right? So that's how we can set up the classes for a grouped frequency distribution. Now let's make a couple of other observations here. First off, notice here I use this hash mark. The hash mark means the word 2. So in other words, the second class would be from 20 to 39 years. All right? So the hash mark means the word 2. Now a couple other definitions here. The cumulative frequency of a class is the frequency of a class added to the frequencies of the previous classes. So in other words, we accumulate the frequency as we go along. Now associated with that, the cumulative relative frequency is the cumulative frequency of a class divided by the sample size and is expressed as a percentage. In other words, as we accumulate the relative frequencies, we get the cumulative relative frequency. That's another way to think about it. So let's take a look at an example and see how we do the computation of the cumulative frequency and the cumulative relative frequency. So how about this? The number of Americans by age group requiring more than a 3-day stay in the hospital in 2010 is shown in the frequency distribution. Let's go ahead and look at that. Fill in the two rightmost columns. And here's some information I got from the Centers for Disease Control. So notice here, there were 122,000 patients that were, under 20 years old, 0 to 19, that required one of these lengthy stays. 75,000 from people, from 20 to 39 years old. And then about, for those from 60 up to 79, a little over, 500,000 and so forth. That's for these lengthy medical stays. So let's go ahead and start to compute the cumulative frequency and the cumulative relative frequency of each class. So over here, I'll put the age group. And over here, we'll start with the cumulative frequency. I'll write CF for that. So those in that 0 to 19 group, well, the cumulative frequency would just be the class frequency. There aren't any classes before that. For the next class, 20 to 39, what do we want to do there? We want to take the frequency of the class, that's 75, and add it to the previous class frequency. So let's go ahead and clear out our previous calculation there. So we'll take 122, add on 75. So we get 197 for the frequency of the second class. And then, for our third class then, we'd want to add on 324 then, right? So we're going to add on 324 to get 521,000. And so there's our cumulative frequency for the first three classes. Now let's do the cumulative relative frequency now, and see how that's going to look. First, what we have to do is to find the sum of all the frequencies. So to get this cumulative relative frequency, what do we have to do? We want to take the cumulative frequency of a class and divide it by the sum of the frequencies. Now, I took the liberty of computing the sum of the frequencies here by adding up the frequencies of each class. So the sum of the frequencies is 1,467. So for the cumulative frequency of the first class, let's go ahead and compute that. We'll take 122, divide that by 1,467, and hit that SD key there. So that would be about 8%. And then for the next class, we'll take 197, divide that by 1,467. So there's our next cumulative frequency. It looks like it's 13%. And let's go ahead and do one more. 521, that's the cumulative frequency of the third class, divided by the sum of the frequencies. And that one looks like it's going to be about 36%, rounded to the nearest whole number percentage. All right, so notice here, we're accumulating the cumulative frequencies as a percentage as we go along with the cumulative relative frequency. So I went ahead and filled that chart in, and there it is all completed for us. All right, so let's make a few observations now on these grouped frequency distributions. First, we round the cumulative relative frequency to the nearest whole number percentage. Notice that's what we did there. We could also compute the class's relative frequency with a grouped frequency distribution as well. In particular, if the data is ordinal level, it really lends itself to that kind of thing. The cumulative frequency is inappropriate for nominal level data, though, the nominal level part of categorical data. And the cumulative frequency of a class is always equal to the sample size, n. So in other words, as we accumulate the frequencies, the last cumulative frequency that you'd write in the table would always be the sample size. And also, related to that, the relative cumulative frequency of the last class is always 100%. Now that gives her, give or take that rounding that we talked about before. So because we've accumulated all the frequencies for all the sample data we have. So there we go. That's how we work with ungrouped and grouped frequency distributions. Let's take a little break, and then we'll come back. We'll talk about how we graph these frequency distributions.